And so good morning, everyone, for our July 7th ME 316 live lecture. Let's see, last week we finished the section on chapter 12, looking at beam deflections due to the bending contribution of that. That homework is due this Saturday over that chapter 12. And again, that's homework. You definitely don't want to wait till the last minute because some of those that you're deriving out, they do take about an hour to do a problem. And then there's a lot of algebra involved in that as you're integrating back through and then solving your constants of integration. So yeah, definitely get a head start on that if you haven't already. I'll be working on grading that last homework you submitted on bending transverse shear, and then also on your first exam. Hoping I can get that to you sometime next week, results on all that stuff. But this week we're gonna then kind of go into the whole failure theories and combined loading topics that show up later on in your textbook. And so let me go ahead and share my screen. And really a lot of this discussion on failure theories kind of then relates back to what you learned in ME 216 with stress, strain being a tensor. You have a 3D state of stress, and you're looking for critical states of stress on other planes within that object, and making use of that then those critical stresses to determine when failure is going to occur. So that's more of our discussion today, is really just that refresher on that content from ME 216, and then we'll talk about failure theories in detail, and the combined loadings more on Friday. And so just with review, these are my lecture notes. I didn't really have to rewrite these at all. These were okay. Just photocopy in. But just recalling from ME 216, you have a potential for a full 3D state of stress. I have the X, Y, and Z axis shown, and so normal stresses face away from the planes. Shear stresses face parallel to the planes. And you can represent that stress tensor in a matrix form at a given point. Your stress matrix S, and sigma X, sigma Y, sigma Z across the diagonal. And then the shear stresses would be symmetric, so tau XY would be equal to tau YX. So that's familiar from ME 216. And then for that special case of plane stress for sigma Z's equal to tau XZ equal to tau YZ, we can look at the sign convention on a positive normal stress and shear stress. The normal stress is easy. We know that if the arrow faces away from the element, that it would be a positive stress, essentially pulling that. If it's facing inward, it would be a negative or compressive stress. Or if you're going through and you have it drawn like this and it comes out sigma X is a negative, you know it's acting in the opposite direction, which is inward, which would tell you that it's compressive. With Hippler's textbook, that always was a kind of a confusion in terms of what is the sign on the shear stress. And when you look at that, the X and Y axis that you've drawn here, if you look on the positive face, if the shear stress is facing in the positive Y direction, so if it's facing in the positive direction for the other one, that would be positive. shear stress, and then if it's facing in the other direction, it would be negative. And so you always look at the positive sides. And so tau yx here, or on the positive side, it's facing in the positive x direction. So those both indicate that's a positive shear stress. Then what I always like to think about that is, if you think of a fuselage of an airplane, it's under some state of stress. And if you cut like a little square out orientated on the XY plane, to keep that under the same state of stress, you'd have to have these sigma X, sigma Y values and your shear stress values to maintain that same state of stress if you were to cut that section out. Then if you were to then say at that same point, cut it out in a different orientation on say an X prime, Y prime plane, that would require different normal and shear stresses to establish that same state of stress on that chunk that you've taken out of the fuselage, just in a different orientation. And so that's really the whole idea of stress and strain transformations, is really just the orientation of that stress element with respect to the X and Y axis. And so this is kind of the start of that discussion, where say we have an angled cut at some angle theta, and we're wanting to know what the sigma X prime, sigma Y prime on our rotated axis looks like. And so here's a diagram then of that angle theta that we just looked at would be the same as rotating our XY axis given angle to the X prime, Y prime axis. And then we're interested in what are those states of normal and shear stress that would be needed essentially to create that same state of stress at that point. Depending on the textbook you're using, some books use normal and tangential for those definitions instead of the X prime, Y prime axes. I can't remember what Hibbler uses, if that's the case. I'm guessing that this is probably referring to Hibbler, but example 2.8, sigma X prime is equal to sigma normal, sigma Y prime is equal to sigma normal. They use that sigma in for both of those to define a normal stress. So there's not that distinction between sigma X prime, sigma Y prime. And so my preference is to use the sigma X prime, sigma Y prime, and tau XY prime. So you have that distinction between those two normal stresses. And so that's the main note, is in general, sigma X prime is not going to be equal to sigma Y prime unless you're at a special angle position where you're perfectly vertical at that point. Perfectly vertical on your Mohr circle. And again, this is a refresher. So if we were to take that element that we had on the previous page, that angle theta, essentially all you're doing is a summation of forces. And so if you look at, say, the bottom side, it would be a sigma y, the differential area times the sine of theta would give us that area on the bottom. And multiplying by sigma y would give us then a force in the y direction. Same thing with our shear stresses. Multiplying those by dA sine theta would give us our force in the x direction due to the shear stress. Then on the cut plane, we just have this being defined as the full differential area. And we'd have our force in the sigma x prime direction and the tau xy prime on that slope surface. And so really, most cases, you're given what your state of stress is, or you've solved for your state of stress. And so you're just looking for what are your stresses on a different orientation at that same location. And so that's our goal then, was summing forces in the x and y equal to 0. We have all the knowns, all the original stress conditions, and we're solving for the unknowns, the tau xy prime and sigma xy prime, to satisfy then equilibrium. And so that's something that you did in ME 216, and you have that relationship for sigma x prime just being the sum of the two normal stresses divided by 2 plus the difference divided by 2 cosine 2 theta plus tau xy sine of 2 theta. Will give you then what the stress is on the reorientated plane. If this is, say, 30 degrees for theta, all you have to do is plug in 30 plus 90, 120 degrees into this equation, and that'll give you your sigma y prime. There's also an expression like this top one that you could solve for sigma y directly based on this same theta value. And so you'll find those in the textbook, as well as tau xy prime, the relationship for solving for that as a function of the state of stress and the new orientation. But this will give you your state of stress along any rotation or orientation. These become important primarily when you're looking at a plane of weakness. Say you have a weld running at a certain angle, you really want to know what the normal and shear stress is along that weld, which would dictate if failure would occur. But if it's just a standard object that's a part that you've designed, what you're more interested in then is what is the critical orientation where you have a maximum state of stress or a maximum state of shear stress type of deal. And so that's a unique angle theta where that occurs. And that gets us into the discussion on principal stresses and your maximum shear stress. Again, reviewing stuff from ME 216. And so again, what we're concerned with are the principal stresses, what are the max normal stresses, and so what that really implies is a derivative. If we take the derivative of sigma x prime with respect to theta and set that equal to 0, that'll give us a value of either a minimum or a maximum. And what we'll find is that that principal angle theta will define as theta p as a principal plane. And so tangent of 2 theta p is equal to 2 tau xy over sigma x minus sigma y. And so you'll have two values separated then by 90 degrees. And so that'll give you the orientation of the principal plane and then the principal stresses on that plane for a state of plane stress, say sigma x, sigma y, have values associated with them. Sigma z is 0, which is still a value, but it's 0 on that plane. But sigma 1, sigma 2, in that case, plane stress, will give you sigma x plus sigma y divided by 2 plus or minus the square root of sigma x minus sigma y divided by 2 squared plus tau xy squared. Will give you then your principal stresses. In that case of plane stress, you still need to remember that you have a third principal stress of 0, because that can become important when you're looking for things like the maximum shear stress. If you order things sigma 1 greater than sigma 2 greater than sigma 3, sigma 1 would be your maximum principal stress, sigma 3 would be your minimum principal stress. And so you'll even see it show up in textbooks like that where tau max then is sigma 1 minus sigma 3 divided by 2. I always like thinking of it as sigma max, the maximum value that you have minus the minimum value, where this is the highest, most positive value or closest to positive value, and minimum is the largest, most negative value, or the value that's closest to a negative value. But that relates then back to the Mohr circle. If you were to draw your Mohr circle related to that, I do have an example coming up, just reminding you on the Mohr circle. But in some occasions, say for example, if you have two positive principal stresses, sigma 1, sigma 2, say 10 and 15 megapascals if you're using SI unit systems, you'd have a third principal stress of 0 megapascals. And so that's what's going to be important, the 15 megapascals and the 0 megapascals in terms of figuring out what tau max is. And so that's why you need to keep track of that third principal stress always, because it can have an impact on your overall maximum shear stress. And then there is a 45-degree difference between the principal stress plane and the shear stress plane. And so just to recap on Mohr circle, say we have a 25 KSI stress and the sigma x or sigma x, sigma y 7 KSI and 12 KSI for the shear stress, all positives. But that also caused confusion for me back as an undergrad in plotting this and figuring out then the rotation that would be needed to get to the principal stress. In your Hibbeler textbook, they kind of show sigma to the right, tau positive down. But I recommend kind of establishing it in this manner, where you have sigma to the right, tau positive going up. And in terms of plotting that, then your normal stress is just based on its sign. And so both of these, sigma x is going to be 25 KSI. And so we're out here to 25 KSI. And then the sigma y 7 KSI over both on the right-hand side from the origin. And then the question always was, well, where do you plot then the shear stress? We have 12 KSI, one needs to be plotted above the axis, one needs to be plotted below the axis. And it wasn't until I was a grad student that I learned this trick in terms of plotting the shear stresses. If you look at the orientation of the shear arrows, say if you're looking at your sigma y, if you look at just those two shear arrows, that would cause a clockwise rotation. And so clockwise rotations get plotted above the axis. Whereas if you look at the x-axis, those two shear arrows would cause a counterclockwise rotation. And so counterclockwise rotations gets plotted below the axis. And then we have 25 KSI and then minus 12. I think the thing that causes confusion with that is, well, one, we know that shear stress is a positive 12 KSI. So which one gets plotted below is it negative, and that whole trick on looking at if it causes a clockwise rotation, plotting it above versus counterclockwise, plotting it below, that reduces all confusion associated with that. That purpose of plotting it above or below really doesn't have an impact on the principal stresses. It only has an impact on your principal plane, the rotation that would be needed to get to those principal stresses. And that's that's important to be able to know that properly, is if it has to rotate clockwise or counterclockwise. In this case, it has to rotate counterclockwise to get to that principal stress plane from this point. The other thing to just be aware of from your Mohr circle world is that the angles are multiplied by 2. And so the angle here would be 2 times the principal plane orientation. So you'd have to divide that by 2, this angle here in the Mohr circle land to figure out that actual rotation. Jordan, do you remember these discussions through ME 216?
Yes, I'm just, so where you're plotting tau going up on that, I remember Dr. Romke's hammering into us that tau always goes negative or goes down. I'm just trying to think, and that doesn't really change much if we change the orientation of the tau axis.
Right. And I think that's really following Hibbeler's definition. But I guess my confusion that stemmed from that is that our tau xy here is on the positive face, going in the positive direction. So we know that's a positive tau xy. But one of these has to be plotted above or below. And so it doesn't really make it clear as to which direction that would be placed. And so if we just define tau positive going up and then have a system to define whether it's plotted above or below, then it'll reduce that ambiguity on what to do with the sigma y 7 KSI if that's plotted above or below type of deal. Because if we look at both of these, they're both a positive 12 KSI. And if we were to look at, say, this side, if we were thinking it was plotted below, we'd be like, well, we have to rotate clockwise, but no, it's plotted above, so it'd still be a counterclockwise rotation to get down to that point. And so that's the main thing, I guess, Jordan, is really reducing that ambiguity in terms of which position to plot those respective points so that you can get that proper principal orientation figured out. But then moving forward, the Mohr circle is nice kind of as a visualization tool and to see essentially that direction that it needs to rotate to get to the principal stresses. But you can also get that directly from the equation as well. Sigma 1, sigma 2 is equal to sigma x plus sigma y divided by 2 plus or minus sigma x minus sigma y divided by 2 squared plus tau xy squared. And that'll come out directly then 16 plus or minus 15 KSI, which will give you 1 and 31 KSI. And so for this case, if we order them from largest to smallest, sigma 1 would be equal to 31 KSI, sigma 2 would be 1 KSI, and sigma 3 would be 0 KSI. And so for this example, I use the sigma 1, sigma 3 terminology. But again, I still prefer sigma max minus sigma min, and you don't really have to worry about reorientation at all. But the maximum shear stress then is 31 KSI minus 0 KSI divided by 2 will give us 15.5 KSI. If you were to just look at the stresses on the XY plane, and that would be 31 minus 1, give you 30 divided by 2 would be 15 KSI. And so on that 1-2 plane, the largest stress that you would get is 15 KSI, but on the 1-3 plane, you would get up to 15.5 KSI. And so that's why it's important to keep track of that third principal stress, because that 0 might be a more critical stress than the other two in terms of a minimum or a maximum. And then 2 theta p is equal to inverse tangent of 2 times your tau xy divided by sigma x minus sigma y will give us 53.13 degrees when we do the inverse tangent. And then we just have to divide that by 2 to find that your principal stress plane is 26.6 degrees counterclockwise. And what that means then is on this view, it would be the 53.13 degrees if you were plotting that on a Mohr circle. But if you're looking at the actual element, it would rotate half that, 26.6 degrees. The second principal direction would be 90 degrees from that, 116.6 degrees. And the maximum shear plane would be 71.6 degrees. For the local maximum shear on the XY plane, you would have to look at that for the other orientation for your max shear on the sigma 1-3 plane. But that's just a quick review on stress transformations and getting that notion of principal stresses again, because failure theories make use of principal stresses significantly. Another topic that I have lots of lecture notes on is the whole 3D stress transformations. The equations I've showed you are for 2D stress transformations where you know that third principal stress. When you have a 3D stress transformation, you have to go into the full invariance of stress. It becomes an eigenvalue, eigenvector problem. And that gets a little bit more complicated. I think they cover that in ME 216, but I cover that again for one of my graduate classes in more detail on multiple rotations, figuring out what the state of stress is based on that, and building that in MathCAD. But just looking at the whole concept of failure theories, that whole process, you typically are looking at determining your applied loads, just the forces on the body, what loading is it subjected to, determine your reaction forces, joint forces, moments, that type of thing. And then from that, you can figure out what your internal loadings are. Once you know your internal loadings, you can transform that state of stress or find your principal stresses. And the 3D just gets more complex in doing that to determine your principal stresses. And then you can apply your failure theories based on your principal stresses. There is some failure theories where you can use your state of stress at the point directly and not have to figure out what your principal stresses are. And so we'll discuss that as we move forward. One question is, will it fail? Yes, if it would fail, you'd have to redesign that. No, if it doesn't fail, does it need to be redesigned or resized? if you're trying to design, say, to a factor of safety of 4, and you end up with a factor of safety of 12, there's a good potential you could reduce down the material, reduce down the weight of it, and still meet your design objective. And so there's some practicality associated with that, dealing with standard sizes. Maybe you're dealing with a nice standard size where you end up with that factor of safety of 12, and moving away from that size would just cause complications on what was just physically available. And so the main thing is that from a design perspective is really the analysis should drive that design. When you're sizing components, you really want to take that into consideration on your factors of safety, and also just with those standard sizes. And so looking at Mohr circle for 3D state of stress, I'm not going to have you do 3D stress transformations, but there are some things that you should be aware of. With the 3D Mohr circle, if you have sigma 1, sigma 2, sigma 3, you would have your local Mohr circles for each one of those 1, 2, and 2, 3 planes. But then you'd have your out of plane 1, 3 Mohr circle 2. And that's where you end up then with your maximum overall shear stress, tau max, occurring at some point. And so the state of stress for your object could be anywhere within the shaded in areas, just depending on what type of orientation you have about all 3 axes. And again, I have that note. If you order those from greatest to least, your tau max would be sigma 1 minus sigma 3 divided by 2. I still prefer sigma max minus sigma min divided by 2. And then you have your special case of 3D stresses where you know what that third principal stress is, the shear stresses are 0. You can use your 2D stress transformations on the sigma x, sigma y, tau xy components. This happens with pressure vessels where you have a sigma 3 equal to a minus pressure on the inner wall of the pressure vessel, and the shear stresses are 0. And so even though it's non-zero, it's still a principal stress, so you can use the 2D stress transformation to resolve those. And that could happen with any type of orientation. So it could be that your sigma y is a principal stress or your sigma x is a principal stress. And so if you are given a situation like that, you should be able to solve what the other 2 principal stresses are. Since one is already a principal stress, you can use your 2D stress transformations for that. All right, so now we get to chapter 10, part B of that chapter. The first part of this chapter deals, I believe, with strain transformation. And then the next part deals with failure theories for static loading. This is another area that Hibbler's textbook just does not cover that clearly. And so these notes really kind of provide insight then on kind of a standard way to go about the process or procedure for applying failure theories. As opposed, what you'll find as you read through Hibbler, they have situations if your principal stresses are positive and negative, do this. If they're both positive, do that. And it just causes a lot of confusion based on having to keep track of your sign in order to determine which process to use. The process I'll show you here, you just keep track of your sign and follow the same process with that going forward. And so what we really run into with failure theories for static loading is just that materials behave differently based on the loading they're subjected to. And so if you have a simple case of uniaxial loading, material is going to behave differently under a biaxial or triaxial state of stress. And so we can look at a special case of that with hydrostatic stresses, where we have an equal pressure on all faces. And we have a uniform compressive stress on each face, sigma 1 equals sigma 2 equals sigma 3. And so those are compressive. We'll just look at the plotting of the magnitude of stress versus strain. And so if you were to do that for a uniaxial loading condition, we're all familiar with the nice linear elastic region, yielding, and then ultimately failure. But under a purely hydrostatic stress, the state of stress just increases without any yielding observed whatsoever. It's just being compressed further and further, and the state of stress keeps increasing and increasing. Again, that would have to be for like a solid object that's subjected to the compressive stress. If there was any type of internal cavities or anything like that, it would just collapse on itself. But the main thing we notice is that it just does not yield. And so what we need to do is find criteria that will help predict yielding for a broad range of stress states. We have a lot of data on material failures subjected to uniaxial loading conditions. When you look in the back of your book, they have the material properties listed there. You'll find those on matweb.com and other textbooks online in the library. But the idea then is really to find an equivalent uniaxial state of stress for your complex loading condition, for your 2 or 3D state of stress. What is that then equivalent uniaxial stress? Because if we know what an equivalent uniaxial stress is, we can compare that to the uniaxial yield strength that we have that data for. And so then we can, once we know that equivalent uniaxial stress, we can calculate our factor of safety as just our uniaxial yield strength sigma y divided by sigma e, our equivalent uniaxial stress. And again, factors of safety, remember, if n is greater than 1, yielding would not occur, wouldn't be predicted to occur, but it's less than or equal to 1, yielding would be possible, and failure could occur as well. And that's a failure due to the stress exceeding the strength of the material, essentially. There could also be failures occurring unrelated to the stress, but to buckling type failure events occurring, where you reach a critical buckling load that could cause a stress that's well below the yield strength of the material. So there's multiple factors to consider, and you'll learn more about buckling. We might have time just to touch on it briefly, but that's a good topic of machine design as well. And so it's really design codes that set that factor of safety criteria that you have to use for your application. If the materials you're using are low quality, which means that there may be voids, there may be a wide distribution of strength for that material. Or if you have like a low level analysis where you're just doing a ballpark mechanics of materials analysis just to get average stresses, that type of thing, you're kind of forced to have a large factor of safety, which will mean it just weighs a lot. Where if you move to more high quality materials, you have better control on your processes so that the materials are more uniform from part to part. And you have a higher quality analysis. You figure out what those stress concentrations are, and have a better handle on the actual state of stress. Then you can have a lower factor of safety for your application, which just generally translates into a reduced weight for that object. The problem with that whole factor of safety concept is it really still doesn't give you a clear idea of what are the chances of it failing. You can have a factor of safety of 2, and there's still a chance of it failing. And so that's where reliability analysis comes into play, making use of statistics and using statistics to kind of control the design criteria. Maybe you're in an application where it's fine if 1 in a million of these parts might fail. You could use that as your design criteria and design the part accordingly to achieve that probability of failure. But that gets a little trickier on the application of the statistics to that type of design. And so that's a graduate level course that I teach that gets more into that topic. And so we kind of focus more on the factor of safety approach. And from an application standpoint, you're typically going to be looking then at the design codes to help define that criteria that you're going to be designing for with that factor of safety. And these failure theories that we're going to be discussing then relate then to solving that equivalent uniaxial stress. And numerous theories have been proposed over the years. There's 3 that commonly show up in your textbooks. The earliest one generally is not on that list. Sometimes it shows up when talking about brittle failure theories, but the Coulomb failure theory was proposed even earlier than this in the 1776 timeframe. Over in Europe, it was where it was proposed, but it looked at just the normal and shear stress on a plane. As we continue on, the 3 common ones that are typically referred to are your maximum normal stress theory that was proposed by Rankine, who was from England in the 1850s timeframe. And that individual essentially stated that the equivalent uniaxial stress is whatever the maximum principal stress is, maximum normal stress. So solve for your principal stresses, sigma 1, sigma 2, sigma 3, and whichever is the maximum value of that. And that's from an absolute value standpoint. So if you have a sigma 1 of 10 and a sigma 3 of minus 20, it would be that minus 20 or 20 megapascals. That would be the equivalent uniaxial stress. What they found is that the Rankine failure theory maximum normal stress really only works well for brittle materials. Brittle materials tend to fail due to the normal stress loading condition and not shear, essentially because of the cracks that occur in there. And then in tension, those cracks get pulled apart and causes that failure to occur. But the Coulomb theory was expanded into Coulomb-Moore theory, the one I was just talking about, and that really works well for brittle materials, more so than the maximum normal stress theory. And so even when you're dealing with brittle materials, you tend to use the Coulomb-Moore for that. But then dealing with traditional ductile materials here in mechanical engineering, when you're dealing with metals, things like that, they tend to follow better the maximum shear stress theory and maximum distortion energy theory. And so first off, maximum shear stress theory was proposed by Tresca, who was from France in 1868. You can kind of see that was shortly after, about 20 years from when maximum normal stress theory came out. And again, from France, this is about the time frame they were designing and building the Eiffel Tower. And so Tresca's theory really came into play in helping to design the Eiffel Tower. And what Tresca proposed was that instead of failing by a normal stress, he proposed that failure was caused by slipping of 45-degree planes due to the maximum shear stress. And what you'll find is that under a pure torsional loading, that failure occurs at about half the uniaxial stress. That's a ballpark estimate. And so if we look at tau max, and my favorite way to define that is sigma max minus sigma min divided by 2, we find that failure occurs at about half the uniaxial yield strength, so sigma y divided by 2. And so what we find then is that our equivalent uniaxial state of stress is just the maximum principal stress minus the minimum principal stress. And so sigma E for maximum shear stress theory is just that maximum principal stress minus the minimum principal stress. And that has been shown to work really well for ductile materials. One, it's easy to use. All you need to know is the principal stresses, and you can figure out what sigma E is. And then it's conservative as well. It gives you a conservative estimate on the strength of the material, so lower than what it actually is. And so you have kind of a built-in factor of safety there with the maximum shear stress theory. Maximum distortion energy theory. This is the bit later in the early 1900s. And you can kind of see this is now getting into that time frame of initial flight. And so all these events of making tall structures and the aerospace really helped drive the need to make the most out of what materials are capable of withstanding. And so the maximum distortion energy theory just pushed the envelope of what materials are able to hold even further. And this one has a ton of names. I think you'll see it as maximum distortion energy theory in your book, but it was first proposed and derived in one method by Huber Hincke in 1904. Von Mises derived it different method in 1913. And I would say it's most commonly attributed then to von Mises. When you look at FEA packages, they'll plot your von Mises stress. And so that's what it's just referring to, the maximum distortion energy theory. And then it's occurring on the octahedral plane, so it's also known as the octahedral shear stress theory. And so 4 different names for the same thing. But what these individuals propose then is that failure is caused by slip along the octahedral planes that occur at 54.7 degrees as opposed to the shear planes, the maximum shear planes at 45 degrees. And since planes are repeated 180 degrees apart from one another, you'd have 4 planes for your octahedral planes versus 2 for your maximum shear planes. And then when you factor in material defects, that type of thing, it just increases the probability that failure will occur on those octahedral planes as opposed to the maximum shear planes. On those octahedral planes, you have a component of normal stress, but you also have a shear stress that's really close to tau max. And so that combination really leads to the failure event occurring at that point. And so solving sigma E for that octahedral shear stress, one, you could calculate octahedral shear stress if you want based on that 54.7 degree plane. And you're really just concerned is if that octahedral shear stress is it greater than the critical? Is that going to cause it to fail? And so if you transform that to the uniaxial yield strength, instead of looking at the shear stresses, you have two relationships to figure out what your equivalent uniaxial state of stress is. And so that based on the principal stresses is just 1 over the square root of 2 times the square root of the differences of all the principal stresses, each one of those quantities squared. And so this is not difficult to remember. So you're just taking the difference of all principal stresses, squaring them, square root divided by the square root of 2. We'll give you your equivalent uniaxial state of stress from von Mises perspective. And then additionally, you can get that from the state of stress directly. You don't have to solve your principal stresses. To do that, it's the difference in all of your normal stresses squared plus 6 times all of your the quantity of all your shear stresses squared, square root divided by the square root of 2. So von Mises maximum distortion energy theory, it has the benefit of not needing to solve your principal stresses. You can just use your state of stress at that point and resolve that. Again, yielding is going to occur if your equivalent uniaxial stress is greater than sigma y. Your factor of safety is going to be your yield strength, sigma y over sigma e. So your uniaxial yield strength divided by your equivalent uniaxial state of stress. And it works really well for ductile materials, is less conservative than the maximum shear stress theory. And so what you'll see is a slight weight savings. You can make your parts slightly smaller with the maximum distortion energy theory than with the maximum shear stress theory. And so let's see, I think we're kind of getting to that point of comparing these. And so it'd probably be better to take a break and then get back at 11 a.m. Mountain Time here, and then go through the application of each one of these to the different types of problems. And then we'll look at the failure envelopes and do an example problem. So let me go ahead and stop sharing. I guess, Jordan, do you have any questions up to this point at all?
No, that seems pretty straightforward. I remember the von Mises stress from ME 216.
Okay, that's good to hear you're learning about that early.
Yeah, he just briefly mentioned that and gave us a homework problem on it.
Perfect. Yep. It's a critical concept, and we'll discuss that a little bit further when we get back here at 11 o'clock. So I'm going to click stop here.
All right. See you in a bit.